Okay, so I'll just kind of jump right in. So I'm going to talk about approximation algorithms for bounded degree local Hamiltonians, which is kind of a big title. And so when I was practicing this talk with my supervisor, he told me to put more context at the start, and I ignored him. So what we have here, I'm just going to jump right in to what a two local Hamiltonian problem is. And so a two local Hamiltonian is just a Hamiltonian that's a sum of terms hij, where each of those terms that's being summed up acts on only 2 qubits. So this is kind of the simplest case of the general class of quantum Hamiltonians. We don't have sort of terms that act on many qubits at a time, only 2, but you can still get entanglement from that throughout the whole system. And so that's why we start with this problem. And so we're going to be looking for the maximum eigenvalue, which is the same problem essentially as looking for the ground state if you're a physicist or a chemist. But we're looking for the maximum because it makes some of the math easier to write down. And it turns out that this problem is difficult in the sense that estimating it to within polynomial error is QMA complete, which means that we don't expect to be able to solve it efficiently. And so for a very small amount of context, this problem applies to like kind of everything from like physics to chemistry to going to the movies with your friends. And so that's why I had trouble putting in context for it. But hopefully you can think of some problems in your life that also apply. Okay, so in sort of the bigger picture of quantum information theory, where does this fit in? Well, it's a type of constraint satisfaction problem. And so when we're talking about classical computation, constraint satisfaction problems are sort of well understood. We know that they're NP complete, meaning again, we don't expect to be able to solve them efficiently in polynomial time. And we have what's called the PCP theorem, probabilistically checkable proofs, which says that it's even hard to approximate them for some approximation ratio. And then we have well-studied approximation algorithms to see how close we can get anyways. In quantum land, we know that it's QMA complete, so that's sort of the analog of NP complete. We don't have a quantum PCP theorem, it's a conjecture. So we don't know if it's hard to approximate them, and we're still looking for good approximation algorithms. So in this talk, I'm going to talk about a series of building blocks from my paper. So first I'm going to talk about the classical max cut question.
Yeah, quick question. I'm actually confused why this is equivalent to a constraint satisfaction problem.
Oh.
Optimization sounds different to me than just a binary. Do we satisfy a constraint or not?
Oh, I see what you mean. Well, so the way that we treat it is the Hamiltonian is like a series of constraints. And if you were to solve it perfectly, it would be like solving all the constraints at once. Does that sort of answer your question? It's not exactly the same as a binary one, but in the sense that you're creating a quantum state that's like a string of states for qubits.
I guess if we were saying that the HIJs for all 0 or 1 or plus or minus 1 or something, you said I want to know, is there a state where I get all of the interaction terms to be negative? That would sound like constraint satisfaction. But even if it's not possible to satisfy all of them, I can still minimize it. Yes.
That is exactly the problem. Yes. Okay. So I think you've understood, and we're just saying it in a different language. I guess it's not the question is not, does there exist a state? It's like, can I find a good estimate of the energy? So we're not just looking for the existence, we're actually looking for the state itself. Is that right?
Helps a little, I'm sure I'll see more as you go on.
Okay, I hope that makes sense. Right. Okay, so I'm going to start out by talking about the max cut problem, which maybe some of you have heard of. That's a classical constraint satisfaction problem, but it sort of gives us the flavor of the strategy. And then I'll talk a lot about my work on the quantum version of that problem. This is also known as the Heisenberg model. And then I'll very briefly talk about my work with more general local Hamiltonians and sort of applying this work to practical physics and chemistry problems, like very briefly. Okay. So the max cut problem is this problem where you're given a graph, which is a set of vertices connected by edges, and you're trying to maximize the set of edges that has a different value at each end of its edge. So in this case, they've done it as a coloring. Where does this go? Okay, they've done it as a coloring. So this white edge is connected to that black edge. This edge is cut, and you're trying to like maximize the number of edges cut, but like this edge is not cut. Okay. And so the way that we write that as a Hamiltonian is up here. So this is an NP hard problem, meaning again, we don't expect to be able to solve it efficiently exactly. But what we can do is find an approximate solution. So the way that Gomans and Williamson approached this is a sort of groundbreaking result in the field, is they did a relaxation where instead of allowing only a bit string for the state Z, they allowed real numbers essentially. And that allows them to write this problem as a semi-definite programming problem, which is something that we do know how to solve exactly. But then the state that you get out of that is a list of real numbers rather than zeros and ones. And so the trick is to round that state back to a valid solution for your original problem. And so Gomans and Williamson showed a rounding algorithm, which is a randomized procedure to take that real number bit string and turn it back, or real number string, and turn it back into a bit string, which gets at least 0.87 of the correct answer. And they're able to prove that. Okay.
So if you for the HG, so the ZIL values for the
This, yeah, Z is so you could say like white is 0, black is 1, and the Z is going to be a string that's labeling each of the vertices 0 or 1. And then when you calculate this energy,
weight.
yeah, the weight. Okay, so I didn't talk about the weight, but it's just like the weight of an edge. So like you could say some edges are contributing more to the energy or less. And we didn't really worry about that in this part, but it'll come in later. Okay. Cool. All right. So now I'm going to talk about the quantum version of this problem. So it's a special case of the two local Hamiltonian problem in general, where for each edge, we're applying this Hij here, where it's just a sum of identity minus XX minus YY minus ZZ. And we're still trying to find the maximum eigenvalue. So this turns out to be also QMA complete in a fairly recent result. And it's an open question whether we can approximate that with an approximation value close to 1. Okay, so that's the problem that we're working on. And some sort of recent update from one of my co-authors actually is the no low energy trivial states theorem, which says that there are local Hamiltonians for which the low energy states cannot be prepared by short depth circuits. This should actually say log depth, not constant depth. So that's my bad. But yeah, so you might be thinking, oh, well, you know, maybe it is easy, but there do exist states for which it's not easy. Not for this particular problem, but it's been proven for other Hamiltonians. So it's a big open question. All right. Okay, so why are we talking about this problem? How is it analogous to max cut? Well, when you're talking about max cut, you're maximizing the energy when you put a different value at each vertex at the end of an edge. But this is a classical problem in that all of the terms in that Hamiltonian commute with each other. So there's no entanglement happening. In the Heisenberg model, this is equivalent to I minus swap. And so the maximum energy for one edge is when you put a singlet state on that edge. So it's sort of the quantum analog of difference across an edge, where when you swap them, it's antisymmetric. And so this is non-classical because the terms in this Hamiltonian don't commute with each other. And so that's how it's the quantum analog. All right. So how have people approached this in the past? Well, here's an example of an SDP rounding approximation, sort of similar to max cut. And so Gerbian and Perec showed that they can provide an efficient randomized classical algorithm to output an estimate of the energy that gets at least 0.498 of the exact energy. Okay, and that's based on an SDP relaxation again over all states, but then the solution they're rounding back to a product state. And that's sort of unsatisfying because you think for a quantum problem, we probably want an entangled state, not a product state. But sort of a key point in this field is that we don't really know how to turn an SDP solution into something that's not a product state. And so that's one of the big things that's being worked on. Okay, and they also note that this is almost optimal for the Heisenberg model, because if you think about the very simple graph of just one edge and two vertices, the best product state gets a value of 2, and the best actual state is the singlet state. The best entangled state, I suppose, is a singlet state, which gives a value of 4. So that gives you an approximation ratio of 0.5. So 0.498 is almost 0.5. It's sort of like this is a solved problem in terms of product states. Okay, so then the question is, can we do better with entangled states, and how do we find a good entangled state? And that's a challenge because most n-qubit states don't have a concise classical description. You can't even prepare them efficiently on a quantum computer. And so actually what we're talking about is ones that we can actually find efficiently. So I'm going to go through an overview of our results from this first paper. So first of all, I've misled you a little bit. So I told you that this 1/2 approximation for the product states is good, almost optimal. It's in fact not optimal on large graphs. And so I told you about the single edge graph, where the best product state gets a value of 1/2. That's true, but as you go to larger graphs, you run into monogamy of entanglement. And so basically, if you have more and more connected graphs, you can't leverage your entanglement very well. And so product states are doing relatively better on larger graphs. And so we were able to show that the best product state always gets at least 4/7 of the optimal value, minus this thing that goes with the size of the graph. Okay, so that's what that is. In our second result, we showed that when we're talking about weighted graphs, if we extend our notion of product state a little bit to say products of 1-qubit and 2-qubit entangled states, then we can get at least 0.5. The best state of that type gets at least 0.55. So we're already sort of surpassing that 0.5 threshold. And we show an algorithm to get at least 0.53, which was the best known at the time. And we'll talk about what's happened since then in a little while. And then finally, we provide a short depth quantum circuit that can outperform all product states, but only for a very restricted class of 3 and 4 regular graphs. And that's mainly because it's annoying to prove it if you don't have that structure. I think it would work in general, but I didn't prove it. So there we are.
So where do these numbers come from? Is it the numerical procedures that you?
Yeah, well, I actually removed that slide because I was going to run out of time. But what you do is you come up with a state that you can upper bound the best value, or the best that you can use to upper bound the maximum eigenvalue. So for example, we could pretend that we could put the singlet state on every single edge. And that would give you an upper bound, because clearly you can't do that, but if you could, it would be better. And so that would give you an upper bound on the energy. And then you find another state where you can lower bound, and you take the ratio of those two things, and that gives you an approximation ratio of what you would get for the best. Does that make sense? So you find a silly upper bound, and then you take like the worst case scenario for your state that you're preparing, and that gives you a lower bound. And by taking a ratio of those two, you proved a lower bound on the approximation that you get. And obviously the game is to get a tight lower bound that you can still prove, right? Okay, so I'm actually going to skip over this first result and just go straight to the second one, because I think it's the sort of interesting intuition in this work. Okay, so what are we talking about here? So this is where, when we extend our notion of product states a little bit, remember in the previous work that was done, they're rounding SDP solutions to a pure product state. So 1-qubit, tensor 1-qubit, tensor 1-qubit. And now we're saying, okay, our little phi states could be a 1-qubit state, or it could be an entangled 2-qubit state. Okay, and so when we do that, we're able to get at least, we're able to show that such a state exists that gets at least 0.55 of the optimal. And we have an efficient algorithm that will get at least 0.5, that will give you a state with at least 0.53. Okay, and that was the best known algorithm at the time. So how do we do this? So basically, you remember that the single edge case is very bad for product states. They can only do 1/2 on a single edge. And so you can imagine a case where sort of the weights of the edges are making your whole graph look like a collection of single edges connected by very low weight other edges, I suppose. And that would be a very bad situation for product states. But we also know the correct answer for that single edge state is the singlet state. So our algorithm is sort of like the very stupidest thing. Well, why don't we just take the maximum weight edge on each vertex and put the singlet state there. And then for everything else, we're just going to give up and put a completely random state, random single qubit state. And we're going to compare the energy that we get from that guy to the energy that we get from other people's rounding algorithms. And so just that little bit is enough to push us over the edge and get a little bit better approximation ratio. So that's the intuition there. And so then that's still sort of unsatisfying because you think maybe it should be, entangled beyond just 2 qubits. And so that's when we move on to talking about quantum circuits. Okay, so our result here is that when you're talking about 3 and 4 regular graphs, so a graph that has, for every vertex, it's connected to 3 neighbors, or for every vertex, it's connected to 4 neighbors, then we have a short depth circuit that will produce a state that outperforms every product state. And so we're going beyond product states with that. And this is efficiently computed as well. So how do we do that? So we're going to start with the state from the max cut algorithm. So remember, I talked about this approximation for the max cut problem, which is an efficient algorithm to produce a bit string that's a pure product state. Okay, so we're going to take that state, and then what we're going to do is we're going to apply this funny gate set to it. So if the qubit in question started in state 0, we're going to apply an X gate. And then for every edge that it has, if the neighbor started in state 1, we'll apply Y. If the neighbor started in state 0, we'll apply X. Okay. And so why the heck would we do that? Well, the answer is if you do that on a single edge, it's going to create a singlet state. And so the sort of intuition is maybe if we do that a little bit everywhere, it'll make everything a little bit more singlety, and that will be good. And so that gives you sort of entanglement across the whole graph. And so you can just calculate out what this guy is going to do. We sort of use a single variational parameter here, theta. So we're going to rotate all of these edges by an amount theta, and it's going to be the same for all of them. So it's sort of like a single parameter variational circuit, if you want to say it that way, but you can just calculate out what it's going to give you. And it turns out that it's 1.047 times the best product state for 3 regular, 1.001 for 4 regular. And you see you sort of got diminishing returns here, which you expect because the product states do better on more connected graphs. Okay, so what's happened since then? So I was lying to you again. In fact, people have found a way to round their STBs to product states, or to entangled states, sorry. So Korek and Thompson had this really cool result where we used just the max weight edge to put our singlet states for our 1 and 2 qubit entangled guys. What they did was they used an SDP to decide where to put their singlet states. And so that's a really cool idea, but unfortunately, it doesn't get us very much farther. They got 0.53 instead of 0.51, or 0.33 instead of 0.531. So it's only a little bit better, but it's a cool idea. And then Robbie King, just like last month, came up with a way to use the SDP to choose the parameters theta for a circuit similar to ours. And so when you use the SDP to choose how much you're rotating each edge towards a singlet, then you can do quite a bit better. So he got an approximation ratio of 0.58 out of that. So since this work, I've actually taken this in a different direction, which is talking about not just the Heisenberg model, but 2 local Hamiltonians in general. And I'm going to go really quickly through this part because we don't have a lot of time for it. But sort of it's sort of the same idea as the previous work, but a little bit more technical. And so if you really want to get into the details of it, unfortunately, you have to read the paper. I know everyone hates when people say that, but I think that's the only way to really get it. So what we show is that if you give us a product state, then we can apply a short depth quantum circuit that will improve your product state by an amount proportional to the variance of that product state. Okay. And so what does that mean? That means if you give us a product state that is already an eigenvector of your Hamiltonian, I can't promise that I'll improve it. For one thing, it might be the best eigenvector. So obviously I wouldn't be able to improve that. you know, and like conversely, if you give us a product state that's like really, really bad, I'm more confident I can improve it a lot. So hopefully that makes some sense. And then also in the same paper, we also show that if you give us an entangled state, we can also apply a circuit that will improve it a little bit. But that circuit might not be short depth, so it's pretty impractical. So I took this stuff and went and applied it to some actual physics problems. I don't know if any of you guys are physicists, but this is sort of what we did, just some really basic numerical experiments. So what you're looking at here is in the top left, we're looking at the Hubbard model. We have a C2 molecule, lithium hydride, and then again, Hubbard sort of in a different case. And on the y-axis, you have the energy of the state. And on the x-axis is essentially just a single variational parameter. And so when you start with the random state with Hubbard, you get this energy. And then we sort of have this cute little trick called theorem 1, where we fix a random state slightly by taking a subset of the qubits and updating their state based on the state of their neighbors. So obviously you can't do that for every single qubit because you like have some sort of recursive thing going on. But if you choose a small enough set of qubits, then of course you can update them a little bit. And so that sort of gives you a little boost. And then this SAC shallow approximation circuit is the circuit I was talking about from here, this theorem. So when we apply that, you can see that we improve the energy significantly for these guys. And then we also applied this. Oh, and so we started from for the Hubbard model, its product state, and for the chemistry molecules, we started from the Hartree-Fock state, which is another easy product state to calculate. And so the deep approximation circuit is the second algorithm I was talking about here, where you can start from an entangled state. But the entangled state, you might not get a short depth circuit. So we started from the product state, and that allowed us to have a short depth circuit. And so we could still use this more complicated circuit for these product states, at least. And so you can see we get some kind of numerical improvement in the energy here, and that's promising, although not necessarily groundbreaking. Okay, so in conclusion, for quantum max cut, we showed that we can sort of get beyond product states by just extending our notion of product states to 2-qubit entangled. And that gives us a way to beat product states over all graphs. And then we also showed a circuit that allowed us to beat every product state, but only for a restricted class of graphs. And again, I think that would work in general. It's just hard to prove. And then when we talked about more general Hamiltonians, we can improve product states by an amount proportional to their variance. And we can also improve other states, entangled states, but perhaps not efficiently. And so will that help us with chemistry? I'm a chemist, so that's why I care about that. And it looks promising, especially because you can just sort of plug and play with these methods with other algorithms that you're using. So you could use this state as an ansatz for another variational method, or you could take the output of another algorithm and stick it into this and see if it can make it better. And so with that, I'd like to acknowledge a bunch of people that I worked with on this. So my PhD supervisor is Professor Jamie Donaldson from the environmental chemistry department. But most of this work was with Professor David Gossett at Waterloo, as well as Anurag Anshu, who's now a prof at Harvard, Mehdi Solimanifar, now at Caltech, and then Kenny Chu and Antonio Mazzacapo are collaborators from IBM who worked with me on the numerical stuff, and of course, a whole bunch of funding agencies.